We are now here with Joep Meindertsma. He traveled all the way from Utrecht. It took him 2 hours this morning, but not because of traffic, but because of the wrong traffic manager. Anyway, Joep is going to talk about atomic data and the semantic web. And I am very curious about who he is. And so maybe please, can you first say something about yourself? And then let's hear it about atomic data.
All right, thank you so much for the introduction. My name is Joep Meindertsma. I'm a software developer and entrepreneur. I did a lot with linked data and the semantic web. And today I'm going to talk about the semantic web and atomic data, which is an iteration on that. So you can watch these slides on tiny.cc/atomic data. There'll be quite a few links in there, so it may be valuable to open it in your browser if you want to. So who recognizes this man on the picture? Okay, quite a few hands. This is Tim Berners-Lee. He invented the World Wide Web, and this is him sitting next to his personal computer showing the world's first World Wide Web page. And when he envisioned the World Wide Web, he kind of had this idea of a very decentralized network. People would have their own servers, and these servers would be able to link to each other, and it would be like this one big equal playing field. Now we're about 30 years into the future, and the world looks a little bit more like this. It has become way more centralized in a way. We have a small amount of actors who have control over a lot of the data. And the nodes between individuals have kind of went missing over time. So what happened is all these actors on the web created their own APIs, their own ways of communicating between client and server. Of course, we still have documents, but the actual application logic commands have become highly proprietary. And that's actually why when you go on Facebook, for example, and you ask for someone's picture, you're not asking their machine to send you their vacation picture. You're actually asking Facebook to send someone else's vacation picture. And in a way, this is really not how the web was intended to work. This doesn't just happen on purpose, which is the case for Facebook, but it often happens by accident. So even when developers create new types of applications, they often end up creating their totally own APIs, which often means that their system isn't very much compatible with other types of systems. This is not because they have ill intent, it's just because it's easier to, do it as you go. So how did we get here? Well, developers have to invent their own APIs. And that's because, firstly, the web is not machine readable. It's designed for documents. The web isn't read-write. It's pretty much only read at the time. However, it wasn't designed to be this way, actually. So the very first web browser had actually full read-write capabilities. So every single web page that you would open, you could actually fully edit. It's a really cool feature. But when the most popular implementation came a bit later, which was Netscape Navigator, which really launched web into, to the masses, because it wasn't just for Apple machines, they kind of left out the write part of the specification and just did the read part. And that's actually the thing that became more popular. And in a way, kind of, it's a bit of a letdown, but we kind of skipped the write part at some point. So I say the web is not machine readable, but to be honest, your computer, of course, can read web pages and it can render web pages. But these are documents. These are not actually data. It's not structured data that your machine can do quite a lot with. And Tim Berners-Lee wanted to fix this as well. And that was because why he basically started with this idea of the semantic web and the resource description framework, or RDF, or later rebranded as linked data. It's just a way to make the web machine readable. So this paper from 2001 described basically his vision for how this semantic web would work. And there's a really funny paragraph. You're not supposed to be able to read it, but it's basically describing how this woman has like a personal semantic agent, and it can make doctor's appointments, and it can give directions, and it can match your calendar with the calendar of the doctor, and it can make, review types of recommendations. And it is really, really powerful system. And today I have this cool square thing in my pocket, and I can scream to it, hairdresser, and the next screen on my phone will be this. So in a way, did we make it? Did we realize this dream of the semantic web? Well, not really, because the semantic web is designed with interoperability as its driving force for enabling it. But what you just saw was just Google having a monopoly on basically all location data and your personal data and your calendar, which is how it can do all these types of things. But Tim Berners-Lee was right. URLs can make data linked, and it can make the web far more interoperable. And we would be able to achieve these same things without a monopoly of Google if we were to use interoperable data. So we have linked data, but why aren't we using these links for everything? Because URLs, we use them for web pages, but we don't really use them for data at all. And this RDF format changes that. So I'm sure most of you will be familiar a little with linked data, but I'm going to walk you through what it means for a piece of information to be upgraded to linked data by basically upgrading one sentence to RDF. So we have this sentence: Joep is born in Baarn on the 20th of January, 1991. You can parse this, you can read this, you understand what it means. The computer can do nothing with it unless you use all fancy AI stuff. But if you put it in the table, like this, you have a name, a city, and a birth date, and suddenly it becomes machine readable. You can query it, you can sort it, you can filter it, you can serialize it to other things. It's great. But actually, it's still a little ambiguous, because who's Joep? Which Joep is he talking about? And where's Baarn? Maybe there are various Baarns. And how do you interpret the date? Is it like the 1st of February, or is it like the 2nd of January? What's going on here? And we can fix these issues by using links, because using links, it's still machine readable, but it's also far less ambiguous, because links can resolve. You can click them, you can open them, you get more information. Even in a global context, URLs are completely unique. They always point to the same specific machine or piece of information. They're also browsable. You can open them and you can see more information. You can see the definition, for example, of what a birthplace actually is. Or you can see you can read more information about what Joep is, or about things about Baarn. And it's far more standardized. So the RDF format looks a bit like this. It's using what's called triples. And triples consist of a subject, a predicate, and an object. You can think of this like the thing, its property, and its value. So here we have 6 triples. They're describing this Joep resource, and they're describing a birth date and a birthplace. And the idea of RDF is that it really increases the quality of data on the web. And with quality, I mean the reusability of it. So we have this 5-star open data model. And here on the left, we have fully proprietary data, like a PDF format, because the format is actually owned by Adobe. Here we have, because it's totally on the left because it's not machine readable. Here we have Excel files, which are a bit better because it is machine readable, but it's still a proprietary format. There we have CSV, which is machine readable, and it's open, so everybody can modify it and use it. There we have RDF, which actually uses links to make it interoperable on the web. And finally, we have linked open data, which is totally usable by the cloud, and it's the best thing ever. So we read about this, and we were really excited, and we went like, yeah, let's go all in on RDF. Because we really believed in the merits of the semantic web, and this should be like a future that we can achieve. So we built this e-democracy tool. It's called Argu, and it's like a software as a service platform that we sell to governments to help them get citizens engaged in politics, so they can like vote, they can have discussions, they can offer their ideas. You can see meetings from governments, all sorts of digital democracy type of things. But the relevant part is everything that you see is actually linked data. So every button as a resource, every single like interaction, every single menu item is actually fully RDF. And we went all in on RDF, but we had to do a lot of things to actually realize this. So first, we had to make RDF work with the React JavaScript frontend framework. It was a big thing to fix. It took us about like 9 months, and a colleague of mine created the link Redux library, which fixes this. We also had to make RDF work with Ruby on Rails, which was our backend system, and we had to write serializers for that and all that. We had to create a lot of ontologies to describe things like what is a menu item, What is a button? What is an action? And how do you open an action? And we had to describe these and share these on the semantic web, of course. We had to invent a new RDF serialization format because the existing formats, there are like 7 or more, because the existing formats just weren't fast enough to run an application like this. We had so many triples going into the client and we had to parse these. So we had to make, optimizations there and create a new format. We had to build dynamic forms from the Shackle specification. And we had to do full text search and map that to RDF as well. So it was like a lot of technical challenges, but we basically managed to tick all boxes. And finally, we got the application working. It took way longer than we should have taken, but it works. We have like a blog if you want to read more about this specific story. But the more we built with RDF, the more I felt like I'm losing hope that this is going to be like the future of the web. And that was kind of a big bummer. And the reason why there is so few linked data at the moment, I mean, less than 1% of data on the web is linked data, it's simply because RDF isn't attractive enough for developers, specifically web developers. And the main reason for that, I believe, is because JSON just won the war. JSON is the thing that most web developers tend to use for pretty much everything. It's what most APIs serve out, and it has a bunch of advantages I'll dive into. So what makes RDF less attractive to developers than JSON? It's not just the lack of tools and libraries, because we actually made a bunch of tools and libraries, and even after we did all these things, we still were left with like a couple of problems. First, RDF doesn't have any form of native arrays or sequential data. It does have models for collections and sequences and bags, but all of these have their own downsides, and it's really, really confusing. I wrote a blog about this specific thing just for myself to understand what it all actually means. And linked lists are the default in many serialization formats. These are actually fundamentally a complex thing because they can point to data on other machines as you traverse the list. So it's really highly unpredictable how slow an operation will be. And also the native arrays, they work very differently in serialization formats. So like JSON defaults to collections, but if you use Turtle, it defaults to a sequence, and it's very, very confusing. That's not a good animation. So the second problem is the lack of subject property uniqueness. And a subject can have many triples with the same predicate. And what this basically means is I can have a Joep birth date 1 and I can have a Joep birth date 2, and these could be different. That's something that you don't typically see in any type of serialization format, but it's actually a very fundamental part of the RDF data model. It makes it very hard to store data in maps, hard to store it in key value stores. And that's a shame because maps are really, really fast, and as a programmer, you really like them. They're also very hard to query, and it leads to a very bad developer experience, especially comparing with something like JSON, where you can just say thing.property and you get the value back. So another problem were blank nodes. And blank nodes are this really complex thing where a resource has an identifier, but the identifier doesn't really exist in a global scale. It's only local. And but you still have to deal with them. And it's basically the server saying to the client, hey, client, here you have this string. Now it's your problem. I'm not going to give Eric any guarantees on this. So probably you're going to have to fetch the entire data again later. This also leads to name collisions and basically a very high cost for clients of the data to deal with. There's also named graphs in RDF, which provide just another layer of complexity. Every time you have a triple, that triple can actually be part of a named graph, which is stored somewhere else. And then you have to resolve that named graph and get that somewhere else if you actually want to access that triple. And there's no consensus on what the best practice is. So developers are using these named graphs for all various types of purposes, like versioning, metadata. We used it for actions. It's like you can do anything with it because there's no consensus. And this all boils down to it's really, really hard to select one specific value. So here we have Joep birth date stuff. And at the top one, there's like a date. And it's part of some named graph. And the second one has like a birth date object. It's a different type of resource. Then we have a string, and then we have another string, but it's a different language. And at the bottom, we still have a different date altogether. And the problem is this is completely valid RDF. And what I want to be able to do is just, give me my birth date and give me a date. But I actually have to do this really, really complex query to deal with all these quirks. And this is a cost for clients every time they have to select one single value. It's a really big cost. And there's also a lack of consensus on usage. So many resources, most notably properties, don't actually resolve. So you have like this property or this predicate, you click on the link and you don't get anything. And that's because some people release their RDF as a data dump. Some use Sparkle or triple pattern fragment endpoints, but don't use actual document resources. So there's a lack of consensus on how to do this. There's also a lot of different serialization formats, which every client will need to deal with. And there are no requirements regarding this as well. And the documentation itself is kind of fragmented because the specification is already now like 20 years old, and there were all these working groups and commissions all doing different things. And it's really hard to, fully understand the entire ecosystem just looking at one document. Finally, a lack of type safety. So if you've ever used something like TypeScript or Java, you get like this type safety in some degree or higher degree. But in RDF, any predicate can have any type of value. Everything can be nullable, everything can be an array, everything can be a string, whatever. You have ways to guarantee this type safety, but these are fully optional and they have their own complexities because they have to deal with the quirks of RDF itself. So what I'd like to have is something that still uses this decentralized semantic web vision of how we could reuse data on different machines and basically treat the web as one big database. So use a lot of URLs, but it should also be easy for developers like JSON, which people already use mostly, and it should be fully type safe, like something such as TypeScript. And basically, what I think is the solution to this is to take a very, very strict subset of both RDF and JSON. And that's what atomic data is. It's just a very, very strict subset of these existing specifications. So if you draw a Venn diagram, you get like RDF link data and a big circle on the top left, JSON on the top right, and then beneath you get like type safety. Atomic data is basically where all these three things are combined. So what you get is fully resolvable RDF. It's fully valid semantic web data. You can reuse this link data, but it's also idiomatic JSON, which means it's pretty JSON. You can easily read it. You can easily parse it. Developers will find it find themselves feeling at home. And it's fully type safe. You get these guarantees that you get a date type or a number type or whatever. How does this work? With very strict properties. So now comes the most technical slide. So what are atomic data properties? They are the things, if you have a subject, predicate, object, you take the predicate and you resolve that, you go to that link, you get a property. And it looks like this. So here we have a JSON LD or a JSON AD representation of one specific property. This is the description property. So it describing things. Maybe a bad example because it's kind of like meta and very abstract. But anyways, we use the JSON AD as a serialization, which is a subset of JSON. The @id is the actual thing that must resolve. So if you open the @id link, you will get this resource. That's a guarantee. Every key will be a property, except for the @id, that's a special one. All the other ones are actual HTTP identifiers that you can click, you can open, and these keys will tell you something about the data type that they will expect. They will give you a semantic description of the relationship, and they will tell you something about the data type. And they also give you a short name. And that short name is important because the short name maps this really, really long URL, which is hard to type, and you're going to make mistakes doing it, to a really, really short idiomatic JSON key. And these are predictable. And finally, we have description. So a description has every property has a description, so it's human readable. You can hover with your mouse over it and you see some more information about what birth date, for example, actually means. So we have properties, but we also have classes. And classes describe basically a collection of properties, like a blog post or a user or an agent. They describe which properties are required and which ones are optional. And they can be used to validate data. They can be used to show forms. And one big difference from RDF is that here these classes are tightly coupled to the actual schema. So if you open the class, you will see the required and recommended properties, which is what is the default in almost every other schema type of language. So the specification is divided into two parts. We have core. The core is like the most important part to get right. It's the JSON AD serialization, the properties, the data types, the classes, schema language, which I've just talked about. And then there's the extended system, which actually allows for authorization, authentication, collections, querying, WebSockets, all this extra type of stuff, which you will use if you want to build a really, really highly interactive web application. So static data is relatively easy, but as we all know, data changes over time. So how can we deal with that? So with atomic data, we standardize changes. Every change is a transaction. Every transaction is actually a resource. And by standardizing changes, you get a lot of benefits. First, we get versioning, we get history, we get global undo for everything. So everything you do, you can undo it, you see your history. That's a really big benefit. We get full verifiability because every change is actually signed with the private key of the one making the change. That means that basically every piece of data becomes a verifiable credential. You have cryptographic proof of who made the change, when, about what. You could share these peer-to-peer. So you could definitely share these like through Bluetooth. Even if the internet is down, you still have the verifiability. So it's basically like Git, but for structured data. So Git is for files and line numbers and folders, but this is for structured data. And what this allows is a fully read-write web where you can collaborate everywhere. Like open the menu of restaurant and you see an error, you could just suggest it and bloop, you suggest the error in the menu, or you can make a change and request that change to be approved. Imagine that that works for like all the web pages everywhere. So these changes are called commits because, you know, Git commits, it's a term we know. And these commits are resources too with their own URL. So you can open them, you can inspect them. And we use the public key cryptography for signing everything. This makes every change reversible, verifiable, and you can share the data peer-to-peer. Agents are the users making these changes. So we have commits, these are signed by agents. And these two, like people or a machine or an API, also have their own URLs. They have a public key, so other people can verify that the agent owns a specific key. And we use this for authorizing requests. And we also have a bunch of other specifications, which I won't dive into now, but it's important that you realize that they exist. Specifications for describing endpoints, which is similar to the Open API or Swagger specifications. There's collections, which means querying, filtering, sorting, pagination. There are invitations for creating an invite URL, which gives specific rights. We have WebSockets for real-time communication, and it's also more performant, by the way. And there's file upload and download. But of course, a specification on its own will probably not amount to much because you need an implementation. That's why I started working on the Atomic Server project. It's a graph database. It's written in Rust. It's really fast. Like the median response time is in the nanosecond range on my laptop. It's a small binary. You can just, download it. It's fully open source. It's got embedded full text search, indexed queries, sorting, filtering, pagination, authorization, authentication, attachments, versioning. Basically, all these features that I talked about are implemented in there because the way I like to write a spec is to do the spec, make sense, try to make sense of the spec, then build it, make sure that it actually works, and then iterate on the specification and keep that cycle really, really close, because I felt like that was what went wrong in the RDF specification. It was too much only specification, too little implementation. And there's also like a front end. It's built in React, and that's a graphical user interface that basically allows you to view all the data and edit all the data, and I'll show it to you right now. So you can actually follow along on atomicdata.dev if you want to. You can also run the server locally. There's a docs link, and you can use either Docker or Cargo or download a binary, whatever floats your boat. And here we have the Atomic Data web application. As you can see, it's just simple web application. It's kind of similar and inspired by Notion. And what I will do now is open the chat room demo invite as a new user. Sorry, press this button. And now I am actually a new user. So if other people have joined as well, I will send hi, Declarative. And maybe some new messages will pop up if other people have joined as well. Anyways, it's also, bonjour, nice, spiffy, amazing. And one of the things here that's pretty cool is I can click on my agent over here, and I can just, edit the name. Whoop, this is Joep. And everything updates live. So like the thing I just wrote will be updated. Everything will update live in the chat room. So this is like declarative chat. Ping, hi there. Okay, great. We also have documents. And documents are very similar to Notion documents. So you can they are block-based. You can add all these kind of rich fields in them. Or you can create headers if you want. You can just type stuff. And all of this is also live synchronized as well. And users can create their own drives, which is like a Notion workspace. Just press this button, and I'll call this Joep's demo drive. I can create a bunch of resources. I can create a document. I can create a folder, and now I can upload files. Like, let me create a screenshot, for example. It's a really boring screenshot. If that's yes. Okay, there we go. And we also have file support. And files are really important because they're not structured, but it's the place where users tend to have like most of their data. So one of the interesting things about how we just created like this invite is that the user itself is actually contained in one key, which is called a secret. The secret contains the URL of the agent, but also its private key. So this private key is very essential to actually signing things. Now everybody knows my private key, yes, but it's my demo user, so you can go ahead and do anything you want. We also have a full text search function, so I should be able to search for the folder I just created. Of course, when you demo live, then things will go wrong. But I've shown most of the features I wanted to show anyway. So it's time for me to go back to my slides and tell you something about getting started. So we have a bunch of libraries that you can use if you feel like, hey, I'm interested and want to play with this as well. There's the atomic lib library, which is a JavaScript, TypeScript, NPM type of library, which contains a store in memory for JavaScript projects. There's the React library, which offers a bunch of hooks and makes it really, really easy to have real-time collaborative applications. Then there is the atomic lib library for Rust. It's the thing that actually powers the server. And everything mentioned, everything shown, it's all MIT licensed, so you're free to copy it and build your own stuff with it. There's also a Discord channel and a very, very big documentation book, which contains a lot of examples and a lot of background stuff. So yeah, thank you for listening. Does anybody have a question? Because I really want to throw this thing. Oh, that's kind.
So B nodes are actually really useful for particularly for things like people or towns that don't have URLs. So do you support that?
I tried to come up with a different solution from blank nodes. So one of the guarantees in atomic data is that every resource actually resolvable. But if you have a resource that you are not actually hosting somewhere because you don't want to have your own server and comply to all the parts of the spec, you can use a local identifier, a local ID. And then that one obviously doesn't resolve to a URL, but it does provide the server with enough information to know, aha, this is a local ID. I'm going to clone this. I'm going to store it on my own server, and I'm going to replicate this, and I'm going to assign a resolvable URL to it. So it's actually possible to, if you don't want to host it, you can still reuse it. Does that answer your question?
Well, it's not exactly about hosting. I mean, for instance, the concept of the poem, The Wasteland, doesn't have a URL. It's a concept, and it might have particular instantiations, but you want to talk about the wasteland as a concept. And so hosting isn't something that you can do with a concept.
I kind of disagree. I feel like we need to host concepts because otherwise the URL becomes meaningless. it can't resolve. People can't find more information about it. There's someone who has to take responsibility and say, I'm going to take responsibility and describe this notion of the poem Wasteland, and I'm going to add descriptions to it, and then we're going to use that URL because it's actually useful. I mean, semantically, I think you're right, but pragmatically, I think we should always use URLs that resolve.
Hello. Did you try to basically you're trying to make a standard next to RDF and JSON-LD and all to create vocabularies in a way?
True.
Did you try to apply your atomic data to, for instance, VOV or DCAT or other standards that's out there that are used a lot? So and was it successful?
I haven't actually mapped any of these standards yet. But I do have, there's a couple of people in the Discord community who also want to try mapping existing specifications and ontologies and vocabularies to atomic data in some sort of deterministic way. So there is some effort being made of machine generating atomic data specifications from existing ontologies. So the specific thing that people are currently talking about is the schema.org one, because it's really highly standardized and commonly used, and it actually has like a couple of machine readable representations that we could reuse and interpret. But I haven't actually tried mapping myself. It's just such a time-consuming task, and I try to focus on more the technical part right now.
Okay. And okay. What's the status of the atomic data? Let's call it a standard. Will you apply it to W3C or something, or is that what's the plans?
It's actually a W3C community group for atomic data, but to be honest, like most of the activity is on GitHub and Discord. And I think at one day maybe I will submit it as a draft W3C specification, but I'm not entirely sure whether that will be the right format to put the specification in. But I'm not entirely sure about that.
Okay, let's discuss it by lunch.
Yes.
Anyone else? Well, thank you very much, Joep, for an inspiring talk on data, linked data, atomic data.
Thanks for having me.
Yeah, maybe a round of applause. Anyone?